Okay, guys, we shall check this question, which is on compressors. This is air compressors from the question paper of August 2022 exam. Okay, we just want to see how to attempt such typical questions on our air compressors. All right, so the first question, it was on 1.1, which is to define the pressure ratio of a stage of a reciprocating compressor. What is it that you refer as the pressure ratio? So as we know that the pressure ratio is simply the ratio of the output to the input pressure, right? So that one is simply the ratio. So this can be the ratio of output, to input, all right, pressure. So we are referring to the output over the input pressure. All right, in a what? In a cylinder. So this is in a cylinder of a compressor. All right, so I think this part we have it, and from our theory, we are supposed to understand this actually taken from your formulas, all right, the pressure ratio. All right, then we have our question here, 1.2, okay? So let us take the information then see what you're given. There we have got a single acting reciprocating compressor with the three compression stages. So it has got three compression stages, rotates at, right? So I just think it is best that we just take our information as we are answering, because we're gonna need this. So it has got three stages. This is a single acting. All right. So the single acting part, remember, it can be double or single. The single acting, I talked about this from our N5, that it affects the speed. All right. Whenever you talk about the speed, you multiply by 2 when it is a double. All right. A single, you just use your speed as it is. So they were given that it's a 3-stage. So X representing the stages. It means we've got what? 3 stages in this case. All right. So for 3 stages, in this case, we have got a clearance. Later on here, we're given that the clearance volume for all stages is 4,5. So there is a clearance there. So meaning to say, you are supposed also to know the sketch of your diagram. If the clearance is what is involved, we shall have a sketch of this nature. All right, so this is just a sketch, guys, of how we're gonna have our information presented. All right, so remember, it's a 3-stage that we are given. So just gonna have something of this nature, the first stage. All right. Then we've got the second. All right, up to the last one, like that. All right. So this is our volume on this side. We are talking about what? The volume. All right. So this is our volume, remember, and this will be the pressure. So this side we shall have the pressure, and we know that this is according to the points. You can just name 1, 2, 3, 4. Then that means this will be 5, 6, 7, 8. Okay. Okay, that is what is important, and also to know that here we are talking about what? The low pressure cylinder. Then we've got the intermediate pressure. Then we've got what? We have got the high pressure. All right, so these are the most important things that you are supposed to consider. And according to our pressures, here we shall have pressure 1 and P1, P8 at the same time, P2 and P7, P2 and P7, here P3 and what? P3 and P6, P4 and what? P5. All right, you're gonna have P4 and P5. All right. Okay, so we said X is equal to 3. That is for 3 stages. Okay, so this is our information that we are given, and it's a single acting. All right, this is a single acting. And remember, we are also given the speed. It was 250 revs per minute. So we do not know when and how are we going to apply this speed. But whenever it is used, we are supposed to be very, very careful on our information. All right, so this is it. And also given that here, the low pressure cylinder, yes, a volumetric efficiency of, take note, the low pressure cylinder is got what? A volumetric efficiency of 0.96. The low pressure, this one is the one that we are given there. We have got the volumetric efficiency there of what? 96%. So we've got 96% there. 0.96, all right? Let us just write as a decimal, the way that we are given, 0.96, all right? Then we also given the inlet temperature and the pressure are 25.5 degrees Celsius and 90,000 Pascal, respectively. The inlet, that is at the point 1. This is our inlet at point 1. We've got the pressure and temperature there, T1, given as 25.5 degrees Celsius. So what you do is that you are going to add 273 to convert to kelvins, and this will be 298.5 Kelvin. Just add 273. And also you're given the pressure at the inlet as 90,000 Pascal. So 90,000 Pascal, you remember our pressure is supposed to be in what? Kilopascal. So we divide by 1,000. Remember your pressure, guys, from your N5 is not changing, all right? Nothing is changing. Only one or two things that you have to consider. Okay, then the high pressure cylinder has a volumetric efficiency of 0.968. The high pressure is the one that we're given here at the end. This one, the high pressure there, we have got the volumetric efficiency there of what? 0.968. Okay, so that's what we're given. Then what else? Then here we are given effective swept volume of and the output of. All right, so we want to be clear here. All right, we want to be clear here. They are still on the what? On the high pressure cylinder. This information here is still under what? Is under the high pressure cylinder. At the high pressure cylinder, that's where we have this volumetric efficiency. Take note, there is a comma here to say it's a continuation. So also this effective volume here is for what? For the high pressure. So we are given the effective swept volume and the output pressure. We are on the what? On the high pressure cylinder here. This one. This is where we are. So here, what we are given also is the volumetric efficiency. All right, we've got the volumetric efficiency there. It was given as 0, that's 0.6. Yeah, 0.6 cubic meters per minute. All right, so this is 0.6 cubic meters per minute. 0.6 cubic meters per minute. It's on the high pressure. And also we're given the pressure there at the end, which means the output, which is what? P4. So that is P4 in that case. We can even list it down here, guys. P4, just know that we've got P4 there, which is, we are given as 5.8 megapascal. Like I said, our pressure is supposed to be what? Kilopascal. So mega, that's times 10 to the exponent of 6. So to convert to kilopascal, you're going to have to 10 to the exponent of 3 times 10 to the exponent of 3. So one of these represents kilopascal. So you're going to remain with 10 to the exponent of 3, which multiplies what? 5.8. So that will be 5,800 kilopascal, like that, okay? So that is what you're going to have on our output pressure from the what? The high pressure cylinder. Now it's done at this point. It's a full stop there. So now we are good here. The compression temperature ratio is 1.4, while the clearance volume for all stage, take note, for all stages. So we've got the compression temperature ratio is 1.4. So the compression temperature ratio, so let us just write temperature ratio. I'm gonna just write like RT. So the temperature ratio is 1.4. So the temperature ratio, it means that is T2 over T1, like output input. All right, so that is the idea there. T2 over T1. Then what else do we have? We are also given here, while the clearance volume for all stages is what? 4,5 of the swept volume. All right, so this is about the clearance for all stages. So remember clearance volume, VC. So they are saying VC is equal to 4,5%. So that's 4,5% of what? Of the swept volume. But this is for all stages. Each and every stage, it is using this condition. Remember, when we had the volumetric efficiencies, they were given per each stage. Sometimes they will give you the same for all the stages. But here we're just given, they were given separately. Now we are given for all the stages, all right? So remember, this can be given as a decimal. If we divide by 100, that will be 0,045, all right, times VS, all right? Remember, this is for all the stages that we are given. All right, then they are saying here, intercooling is perfect and the pressure ratio is the same in all stages. All right, so if the intercooling is perfect, what does it mean? These are conditions for minimum work done or maximum efficiency. If the intercooling is perfect, it means at those conditions, the work done is minimum and we have got maximum efficiency. And we're given that the pressure ratios there is the same. The pressure ratio is the same. So let us just write here, RPS, which is our pressure ratio, is the same. Is the same for all stages. All right, this is for all the stages that we're given. We have got same pressure ratio. Okay, then what does it mean about the pressure ratio? Remember, we talked about this pressure ratio before, output over input. Output over the input. So you're supposed also to understand that idea of what the pressure ratio, and also I'm going to show you from the formula sheet, the use of your formulas as we are answering our questions. All right, so this is the information, guys. Let us see and try to attempt our questions. So there we are given that, okay, this is it here. 1.21, calculate the stage pressure ratio and intercooler pressures in kilopascals. All right? The stage pressure ratio and the intercooler pressures in what? Kilopascal. As we know that our pressure is supposed to be what? In kilopascal. All right. So what do we refer as the intercooler pressures? The intercooler pressures, we are referring to these pressures at this stage, P3 and P4 in this stage, P2 and what? And P3, I mean. All right. These are the intercooler pressures, P3 and P3. P3 and P2. So you're supposed to calculate this P2 and P3 pressures. Okay. So we have got two things to consider, the pressure ratio and the intercooler pressures. Okay, for the pressure ratio, we also have, we have got this formula. So let me just write this down so that I can show you the formula sheet also. So this is 1.21. All right, so I'm going to show you the formula sheet so that we move together. So if you check here, there is this part of our formula sheet. All right, let me put this one. Okay, we have got here RPS for the what? For the pressure ratio here. They are saying that RPS is equal to the x root of P, the square root of Px plus 1 over P1. Okay, let me explain this formula that we are given there. You have to understand your formulas, guys. All right, they are saying that in order for us to have the pressure ratio, we are supposed to find the x root of, this is Px plus 1 over P1. All right, this P1 is for the inlet. Then Px plus 1 is for the stage. X is the stage. Remember, we've got how many stages here? 3 stages. Our x is equal to 3. So if we add this one, is going to be what? 3 plus 1, because we've got x as what? X as 3. So this will be px plus 1, which is px plus 1, which is 3 plus 1 is what? It's 4. So meaning to say we are talking about P4. That's why we talked about the ratio of output over input. That is where it's simply coming from. X plus 1, where we are talking about the number of stages there. So it means our pressure ratio is going to be x, which is 3. So it's going to be the cube root of P4. Remember, we said Px plus 1, x plus 1, 3 plus 1 is 4. So it's P4 over what? Over P1. So this is simply the cube root of P4. Remember, we have these pressures here. We are given P4, 5,800 kilopascal, P1, 90 kilopascal. So we are simply substituting our values, 5,800 over 90. So this was going to give us the pressure ratio. That was going to be 4,00923, which is simply 4009. All right, as your pressure ratio. So it means wherever we need the pressure ratio, we are going to use this. All right, that is the idea there. So this is what we were given on this question here to calculate the stage pressure ratio. And now they need the intercooler pressures in kilopascal. And I said the intercooler pressures, we are referring to this part of what? Of the intermediate pressure, the intermediate stage. We are talking about P2, P3. So how do we calculate P2 and P3? That is the question. How are we going to have this? All right. There is this formula that we are given. Let me go back to the formula sheet also. Then I'm going to explain this about our pressure ratio. All right. If we go back to here, we are given a relationship that is going to happen between P2. All right. P2 and P3. This one, P2, it goes of P1 and P3. So this one is not going to work for us because we do not have P3, even though we have got what? P1. All right. Then there's this formula about the pressure ratios. This one, let me write it because here we are not given. It states that the relationship that happens from this pressure ratio, it can give us the second pressure from the first one that you are given. What am I trying to say? With the pressure ratio, it follows that if I want to calculate P2 or P3, whatever that I want to calculate, the pressure ratio is equal. Remember, we said it's what? Output over input. Remember, this is what we said, isn't it, guys? This is what we said. This was our definition from 1.1. The ratio of the output to input in a cylinder. In which cylinder are you considering? In which cylinder? Guys, we must understand this. Since we okay, what are we given? Let's start with this one. We want to remember, we want to calculate what? P2 and P3. So in order for us to calculate P2, we have to consider which cylinder and what are we given. All right. We do not have P2, we do not have P3. We have got P1. So meaning to say, considering this cylinder here, the lower pressure, this cylinder, our output is what? It's 2. Our input is what? It's 1. So from that pressure ratio is going to be output over input. P2 over P1. We have P1. So you can take advantage of that. Output over input. So it means we're going to have our pressure ratio as RPS from the first cylinder. So you're going to have output, it's P2. The input is P1. What do we want? We want P2. So you can calculate P2 from there by making this the subject. If we cross multiply 1 times P2, it's P2, which is equal to the pressure ratio times what? Times P1. So meaning to say it's just a matter of substituting in order for us to obtain P2. So P2 is going to be the pressure ratio that we calculated here of 4,009 times P1. What is the value of P1? We have the value of P1 here. We are given the pressure one as what? 90 kilopascal. Remember, our values are given in are to be given in kilopascals. So you multiply by the value that is already in what? In kilopascals. In kilopascal, because the answer is needed in kilopascal. So this was going to give you something like 360,81 like that kilopascal. We have P2. Also, we said we need what? P3 for the intermediate. We also need what? P3. From the same ratio, RPS is equal to the pressure ratio. It's output over input. Where do we have P3? Let's go and check. Where do we have P3? Here. This is where we have P3. P3 is on this one. If we consider here, this is where we have our P3. And P3 is the output in this case, all right? Take a closer look. In this cylinder that we are considering, it is the output there. Okay? It is our output here. This is the input now, and this is our output in the intermediate. Like we said, input, output. So this is now the input, and this is being our output. So the ratio states it's output over input. So our output is what? P3. Input is what? P2. So it's going to be P3 over P2. Let's write our formula here. This time, it will be P3 over P2. As we can see, we have a formula there, and we can calculate whatever that we want. So making this the subject, if you cross multiply 1 times P3, that's P3 is equal to the pressure ratio times what? Times P2. And we calculated P2. Now we got this value. The pressure ratio is not going to change. 4,009 times the value of P2 in kilopascal, since our answer is needed in kilopascal. This is our P2, which we got there as 360,81 in kilopascal. So this was going to give us the value of P3, which is 1,446,487. Sorry, this is 487 kilopascal. The ratio of the output to the input. The ratio of the output to the what? To the input. At a certain stage, for a given cylinder. Which cylinder are you working with? What is your output there in that cylinder? Our output in the first cylinder, which is our low pressure, the output is P2. Input is P1. In this intermediate, P3 is now our output, P2, input. The same in the high pressure, P4 is the output, P3 will be your what? Your input. Okay? So we have to be very, very careful in our simplification that you will be given. It's very, very important that you understand the questions. How are they given? How are they given the questions then? All right. So that was it, guys. In case of needing to use these values, you're going to check them. Let's see this one. Now they need us to calculate, this one is a straightforward. The index of compression, correct to 2 decimal places. So the index of compression is represented by what? By N. We need N. Remember our index of compression from our N5, we talked about this, N. So where can we obtain the value of N? We need the index of compression. All right, let me just write it here and see what we can do. All right, so some of this information we might need it, just recall the values that we got. We might need to use some of these values. As you can see, guys, it's Power Machines N6. A lot of space needed. So I just hope you understand me. All right, so this is 1.22. So what is the value of N? We do not know. That is the compression of index. So whenever we are given this type of a question, we have to check, this is it, where there is N on our formulas. Remember, these are what? Compressors, air compressors. air compressors, meaning to say our gas laws are still applicable. Remember our gas laws wherever there's N. So we have to think of a part where we have got what? N. Okay, so here, this is it. Let's check where there's N, okay? It's unfortunate that I did not insert the other piece of the formula sheet. But if we check from our law, from our gas laws, remember we had our gas laws, guys. There is T1, there is P1 here. There is P2, we calculated P2, or we are given P2, remember? No, we calculated P2. I still have to remember from that value of P2. We had the value of P2, remember? P2, we calculated, it was 360, 360,81 kilopascal. We have this one. And for temperatures, we do not have T2, but there is a temperature ratio, this one. There is a temperature ratio, meaning to say output over input again, T2 over T1. Okay, so if you get back to our N5, all right, this formula, we have it from our first page. I want you to check from the first page of your formula sheet. I did not insert this one, guys, just pardon me. But if you check the first page of your formula sheet, all right, I want you to check the first page of your formula sheet. There are formulas for gas laws there. In terms of where there is N, where there is this N, there's a formula that is given there as T2. If you check properly, I want you to check on your formula sheet, page number 1 is given as T2 over T1 is equal to V1 over V2 to the exponent of N minus 1, which is equal to P2 over P1 to the exponent of N minus 1 over N. Like I said, compressors, these are applications, direct applications of what? Of gas laws. So meaning to say we can use this formula. I think where there's N, that is the best formula that we have, guys, in our formula sheet so far. But we do not have the volume, so I'm not going to talk about this part of the volume. I'm going to talk about these two. So I'm going to equate these two. T2 over what? T2 over T1 is equal to this. So there is an N there. Okay, but there's guys, as you can see, there's a lot to be considered there. Okay, let's get back to this. We said T2 over T1, we do not have, but what does it mean? T2 over T1 is our pressure ratio. Remember, we're given that pressure, the temperature ratio. So T2 over T1 is our temperature ratio of what? 1,4. So we have the value there. We're just going to substitute as it is. Our temperature ratio. So this is our temperature ratio is equal to, what does P2 over P1 represent? That is our pressure ratio, output over input from the first cylinder, our low pressure. Output over input. So there we've got the pressure ratio there. All right? So instead of you looking for P2 and P1, do you have the pressure ratio? Yes, we have that. So it's just a substitution that is happening here. All right? Remember our pressure ratio, guys, we calculated, that was the first question that we calculated. I still remember we got something like 4,009. That was our pressure ratio. So we are just substituting the temperature ratio, which is 1,4. In place of the temperature ratio, we're going to substitute 1,4. So 1,4, our temperature ratio is equal to the pressure ratio. Our pressure ratio, remember, we got 4,009. So this is 4,009 to the exponent of what? N minus 1 over N. Guys, this is N6. This is no longer N5 where we play around with those logarithms, those basic logarithms. Now, we are now applying our logarithms, but the advantage is that the power machines is done on this stage. This is now you and your mathematical calculations now. This is you and your mathematical calculations. What am I trying to say? How can we find N? We can introduce our logarithms. It's either you can introduce as a ln or as a log. Remember, if you're given an exponent, you can introduce what? Logarithms. All right, so introduce logarithms, introduce logs. Okay, so meaning to say we are going to introduce our logarithms there. Okay, so meaning this is a log this side, that's a log this side, and also this is a log this side. Well, how do you understand your logarithms? How do you understand your logarithms? Okay, we know that if a log is being introduced here, we can drop this exponent on a log. The logarithm of m, all right, or let me just write as a to the exponent of m, or any like this, is equal to n, the logarithm of a. The exponent can be used to multiply the logarithm. So meaning to say here, I'm going to remain with the logarithm of 1,4. But this side, I'm going to drop the exponent. So it's going to be n minus 1 over n, the whole exponent as it is, multiplying the log of this times the log of what? 4,009. Remember, what you want to calculate is n, but check what is there. Check what is there. What can we do? So it's up to you. We can cross multiply to remove our fractions. We can, guys, this is now you and your mathematical calculations. But as for me, I always say, avoid simplifying logarithms. Log 1,4 is this log. No, avoid that. Use exact values. So to use exact values, you get exact answers. So this is same as over 1. So I can cross multiply here by n. So this will be n times the log. So it will be n log 1,4 is equal to, here I'm going to remain with what? With n minus 1, since this n is multiplied this side. So here I'm remaining with what? With n minus 1. So the log of 4,0 for this one is going to multiply everything. So it's log times this. So it's going to be n, the logarithm of 4,009. All right. Then we multiply the logarithm of this to what? To minus 1. So it's minus the logarithm of 4,009. So take note, this n is already used. This is the one that we multiplied this log by cross multiplying. Okay, so this is what you're gonna do. Since we want n, and you can see there's n here, and there's also n here, we're gonna collect the terms with n to one side, transpose to one side. So it will be n, the logarithm of 1,4 minus n, the logarithm of 4,009 is equal to, it means we're going to remain with minus this, all right? Minus the logarithm of 4,009, all right? There's an n here, which is common. So what do? I factor out that n. By factoring n, I'm remaining with log 1,4 minus the logarithm of what? 4,009, because this n and this n will cancel. All right, this n and this n will cancel. So I'm just going to remain with log 1,4 and this, which is equal to the minus log 4,009. All right, since we want to calculate n, what do you think we're going to do? Just have to divide by the whole of this bracket. So n is going to be the minus log 4,009 divide by the whole of this bracket, which is the logarithm of 1,4 minus the logarithm of 4,009. So this is you and your calculator now to find this from your calculator. That was going to give us something like 1,31981, something like that. So this will actually change into 1320. The 9 is going to change, so it will be 20 there, which is simply 1,32, right? So you can simply write this as 1,32. That's our n. All right, which is what? The index of compression. The index of compression. So guys, we have to be careful. We have to be careful. Guys, we have to be careful. We have to be very, very careful in our in our simplification. How do you answer your questions? All right. And also your mathematical calculations has to play a role also. All right. It's not about just the power machines. I have to know the formulas. No, your mathematical calculations also must also assist you to find this. So there we just took this formula from our gas laws, right? This formula, I said page number 1 of your formula sheet. Check this formula. But also with our understanding, we reduced this. It means what? The temperature ratio. P2 over P1. What does it mean? What does it mean? Pressure ratio. Output over input. You see now. So that's the idea now that you have to apply. Guys, this is N6 and we have to be also, we have to try by all means to be open-sighted as we are answering our questions. Apply everything that we had in N5. Everything. 1.23, the effective swept volume and swept volume. So this is, we need the effective swept volume and the swept volume of the high pressure cylinder in cubic meters per cycle, per what? Per cycle. The speed has to be involved now. Per cycle. Per what? Per cycle. Where? At the high pressure cylinder. Okay. That's why we took this information about the high cylinder, this one, about the high pressure cylinder here, where we are given the volumetric, the effective volume and the volumetric efficiency at the high pressure. Remember, this was for the high pressure only for the high pressure. Just for the high pressure only. Okay, so the question is saying, for that same high pressure that we are given, this one, we are supposed to calculate what there? We are supposed to calculate the effective volume, but in cubic meters per cycle. Per cycle meaning to say, we are not considering the units, just cubic meters. We have used the speed have been applied. Remember, the speed is one that is taken revolutions per minute. Those are cycles, revs. So it's per revolution, per each revolution. And also the swept volume at the same time. These are the two things that we need. All right. So someone will be asking, why are they saying calculate the effective volume? While the effective volume is there? Yes, it's there. This one, we can see it. But is it per cycle? No, it's not per cycle. Our effective volume, yes, we are given there. This is something that we have. We can see properly. See, this is our effective volume. We are given for the high pressure, isn't it? This is the one. We have them. But it's in cubic meters per minute. Take note. All right? So we have the effective volume as 0.6 cubic meters per minute. All right. Let me take the speed first. Remember, it's a single acting, and I said, if it is a single acting, you use the speed as it is, all right? A double acting, that's where the speed is being multiplied by what? By 2. So the speed here is going to remain as it is, 250 revs per minute. Let me take the speed first. I want you to understand me. So we have the speed there of 250 revs per minute. All right. Okay, this is what it means here. I explained this in N5. I just hope you were with me then, by then. I said that the speed that you are given in revs per minute, it's a neutralizer. What am I trying to say? It neutralizes our units to the unit that is required there. Okay. We need cubic meters per cycle, meaning to say it's cubic meters per revolution, per each revolution, per each cycle. But there it's cubic meters per minute. So guys, there's a need for you to play around with this formula here. We just need to play around with this too to get the cubic meters per revolution per cycle. So this is it here. Let's write our units. Cubic meters per minute means over a minute like this. All right? Revs per minute, it means revs over a minute like this. So here, in order for us to remain with the cubic meters per revolution, which is per cycle, which is the way where the answer is needed, what do you think we're going to do here? Because this one is already in cubic meters, but it's per minute. So this per minute has to cancel with a minute. So meaning to say we are supposed to multiply with minute per revolution. So we must interchange this to give us minute over revolutions. If we can do that, the minute and the minute will cancel, meaning to say we are left with the cubic meters per what? Per revolution. Cubic meters per what? Per revolution. So in order for us to have this, we must change this formula into what we need. The minutes on top, the revolution, because this is 250 revolutions per minute. So it means on our calculation, this is what's going to happen. Our effective volume is going to be the effective volume per minute, 0.6 cubic meters per minute, like I explained, times a minute per, so it's going to be 1 minute because this is 1 minute. So the 1 minute is here, this is 250 revs per minute. Per minute means per each 1 minute, one, and so on. So it's going to be 1 minute over what? 250 revs, because we need minute per rev, per revolution. How many revolutions are there? They are 250. So the 250 is going to be in the denominator, so that the minute and the minute will cancel. So our answer is going to be cubic meters per revolution. That is cubic meters per cycle. So meaning to say we are simply multiplying 0.6 times what? 1 over 250. And our answer is going to be cubic meters per what? Per revolution. Meaning to say we are talking about cubic meters per what? Per cycle. So if we simplify this, 0.6 times 1 over 250, we are going to obtain something like 2.4 there. That's 2.4 times 10 to the exponent of -3. That's cubic meters per what? Per cycle, per revolution, per cycle. Guys, per cycle means our volume is just like, per cycle does not affect. It simply means our volume is in cubic meters there. Per cycle, we do not have units there per cycle. There is no unit there. Okay, I just hope, guys, you understand me. I just hope so. We shall have more questions, but for now, I want you to understand this for now, all right? More to come as we are revising. So that was for the effective volume. What about the swept volume? Okay, we are given the volumetric efficiency here. So from our volumetric efficiency, I want you to see this formula. It's, this one is an advantage. We have it from our formula sheet. Take note. Let me go back here. We are still at the high pressure. That's why I'm using this efficiency. Because remember, there's another efficiency, but it's for the low pressure there, this one. We are on the high pressure cylinder, so we have to use the volumetric efficiency for the what? For the high pressure cylinder. All right, so like I said, from our formula sheet, I want us to check properly about these volumetric efficiencies, all right? How are we given our volumetric efficiencies, all right? This is here. I just hope I inserted that. All right. Supposed to be on this page. Sorry for that. So it's here. Just hope down here. Sorry for that, guys. What happened with my formula sheet? Okay. All right. All right, this one here. All right, these ones here. Differential volumetric efficiencies, these ones. So they are saying the volumetric efficiency, all right? So the volumetric efficiency is given as the volume of air taken in. The volume of air taken in, which is the free air at free air conditions, which is our what? Our effective volume. That is the volume of air taken in. The volume of free air over the swept volume. So this is our formula for the volumetric. So if we check, the swept volume is there because as we want to calculate what? The swept volume. Remember, this is what we want. Let's go back to our formula here. Let's go back to here, to our information. We want to calculate what? The swept volume. So they are saying, if we are given the volumetric efficiency, we are going to use the formula. The volumetric efficiency is what? The volume of what? The free air over what? The swept volume. So this is what we have. And we, for that particular stage, we are dealing with the high pressure. Remember, we are on the high pressure cylinder. What is our volumetric efficiency there? 0,968. So meaning to say 0,968 is equal to, okay, take note. Our answers are needed in cubic meters per cycle. Take note. So are you going to take the effective volume, which was in cubic meters per minute? No. Because if you take that, it means your answer for the swept volume is also going to be in what? Cubic meters per minute. The unit that you use is the same unit that you get on your answer. Are we together there? The unit that you use is the same unit that you get on your answer. Since we need our answer in cubic meters per cycle as it is given there, meaning to say the effective volume that we are going to use is that one that we calculated in cubic meters per cycle, this one. And we got this in cubic meters per cycle as what? 2,4 times 10 to the exponent of minus 3. So it means we are going to use 2,4 times 10 to the exponent of minus 3 cubic meters per cycle. It means our swept volume is going to be also in cubic meters per what? Per cycle. Just like that. All right, so you can cross multiply here. 0,968 times Vs is gonna be 0,968 times Vs, which is equal to 2,4 times 10 to the exponent of minus 3 if we multiply by 1 this side. So to find Vs, we can divide by 0,968 divide by 0,968 this side. This is gonna give us the swept volume. As we used the effective volume in cubic meters per cycle, it means our swept volume also is gonna be in cubic meters per cycle. And that was gonna give us something like 2,479 times 10 to the exponent of minus 3, which is in cubic meters per what? Per cycle. Like I said, the cubic meters per cycle is just cubic meters. There is no need for even you to write cubic meters per cycle. It's just like that. It's just like that. All right? It's just like that. Okay? So we have to understand, the idea there. Okay? Be careful there. All right, guys, I just hope you understand me as we move on. We are still together at Math Zone African Motives till we write our exams. So we just hope everything is going to be okay as we move on. All right, then this one, they need 1.24, the compressor absolute delivery temperature. The compressor absolute delivery. Absolute. Which means we're now talking about the whole of it at the end, which is our T4. Remember, this is the last temperature there at the end is what? At the deliver, there's T4. This is our deliver. So we have got the inlet and also the deliver of the whole compressor. Guys, let me remove some information here. You see, like I said, N6, guys, we've got a lot of things. So just be patient also. So that I will be able to explain my idea as it is to you guys. Okay, this is it here. So remember, they want the overall, like, that is the output of everything, all right? So that's our T4. That was 1.24. 1.24. Okay, so this is it here. We want to calculate T4. And remember what I explained before. Remember what I explained before about the temperature and pressure ratios. Why am I talking about that? Because we have T1. As for temperature, this will be the inlet. All right, this is our inlet temperature. And this is at the deliver, which is our outlet. So it means if we consider that, we will see that in this case, we can have from our temperature, because we've got temperature ratio there here, where we said we can use T2 over T1 for the stage that you're given. So what if we take it from T3, or T2 and because here we've got T3, T4, and T3. All right? We've got T4 and T3. Input, output from the temperature ratio. So let me write it here. From our temperature ratio, I said it's output over the input. So the output being T4, the input being T3. So it follows that at these stages, remember that T1 and T3 will be the same. T1 is equal to T3. So if T1 and T3 are the same, it means we are simply going back input over output, isn't it, guys? This is it. So we simply have this as output over input. Instead of us having this as what? As T3. We're going to have this as what? As T1. For the output, for the input. Inlet to the delivery. Output, input. So we can calculate T4 from there. We can calculate T4 from there. Remember, we have got the temperature ratio. It was 1,4. 1,4, our temperature ratio is equal to T4, which is the one that we want to calculate the output over T1. Why talk about T1? Because there we have this value of T1, which is 298. So that's why talking about this, we have this value of T1. Okay? Use the information that you are given. Always try by all means to use what you are given. Okay, so you have to be careful of what you're given. All right, so this was 298, isn't it? 298. All right, sorry for that. This just changed everything, that every setup that I had just changed. You see these softwares, guys. So that was 298,5. All right, so this is over 1, so you're just gonna cross multiply everything. 1 times T4, that's T4 is equal to 1,4 times this value, which will be 417.9 kilopascal. I mean kelvins, because this is what? This is temperature. All right, but I said also previously that these these compressors, we can also take advantage of our gas laws. All right, remember from our applications of our gas laws that we have got this formula. I used that formula previously. If you still remember, I used this formula. T2 over T1 is equal to P2 over P1 to the exponent of n minus 1 over n, whereby this is representing what? Our temperature ratio. So instead, we can have it as what? As T4 over T1. Output over input is equal to P2 over P1, which is our pressure ratio, which is RPS, our pressure ratio. And remember, our pressure ratio, guys, from our information, our pressure was 4, something, 4, remember here, 4,009. That was our pressure ratio, 4,009. So you can even use that as it is our pressure ratio, which is 4,009 to the exponent of n. And also we calculated n. Remember, we got our n as 1,32, our compression of our compression index. So you can even calculate T4 in this case. If you cross multiply, let me just save it properly here. So it means if you cross multiply, this will be this side. So T4 is going to be equal to T1. And remember, T1 is 298. So it's going to be 298,5 times this value. So that was still going to give us the same value for T4. All right. This is a single term as it is here. So you're going, or if you use this one, it was going to be 417.96 Kelvin. All right. So this one was going to give us this, and this one was going to give us this. As you can see, it's just one and the same thing that we are having there. Just one and the same answer there. So that's how you play around with our formulas. All right. So I want you to be careful with how you take your formulas. All right. How you take your formulas is very, very important. Then Another part, which is actually the last part, and it has a lot of things that has got 6 marks there. They want us to calculate the induced volume, swept volume, clearance volume, and the cylinder volume of the low pressure cylinder in cubic meters per cycle again. Take note. In cubic meters per cycle, I explained about this part, but they are saying for the low pressure, meaning to say we are working with this one, guys. I'm just going to remove these values. We know them. Okay, we talked about this. No, these ones, we need them. All right, these ones, we need them. Let me just push this one. I'm just going to list what you're given there. All right. Sorry for this, guys. All right, let me just put it here. Do we need this? We're not going to need this. So remember what we are given to calculate. That's 1.25. I'm just going to try to have this. We are asked to calculate the induced volume. All right, the induced volume. This is the induced volume. It's given like that. All right. Also, they wanted us to calculate the swept volume, the clearance volume. All right. Is it everything? I think there were 4. Is it 4 or 3? The effective, they said, induced volume, swept volume, clearance volume, and the cylinder volume. All right. So you also need the cylinder volume and the cylinder volume. All right. The cylinder volume. All right. So this is for the cylinder volume. All right. So these are the 4 volumes that we are supposed to calculate. Okay. What is it that we are representing? Remember, this is for the low pressure cylinder. The low pressure cylinder here, this is where we are talking about here. And in order for us to have the induced volume, this is, it indicates V1. That is the induced volume. It indicates V1. So from our gas laws, remember we had those gas laws, pressure, volume. Remember, we've got these formulas from our first page. We've got P1, V1 over T1 is equal to P2, V2 over T2. Those are the formulas that we can go back and think about when you are calculating the induced volume, which is our V1 in that case. So this is the induced volume. All right, this is the induced volume. Do we have, in this case, T1? All right, do we have T2? So this is what is going to happen. When this is T1, this is V1, this is the induced volume. But on the other hand, if we check, we do not have V2. Yes, we've got P2 and T2, but we do not have V2. So it means this is going to limit us. So what do? We have to equate to any part that is complete. P3, V3, we do not have V3. P4, V4, what is written is the effective volume. T4, we have that T4. So meaning to say the one for P4 times the V4, which is the volume there at the end is what? It's VE. It's supposed to be over T4. Guys, what we want is this to be equated to any other pressure. It's not to say when they are saying for the low pressure, the ratio is supposed to be here only. No, it can be equated as long this is from the low pressure to another one. It's fine. So what we want there, we have got everything here. But if we consider this, they want us to calculate all these in cubic meters per cycle. So it means we are not going to use this VE in cubic meters per minute, this one that we are given. No, we are going to use that VE. Remember, we calculated the VE before. I think we removed that information, but it's fine. I'm just going to have it down here. Remember, we calculated our VE when we calculated per cycle, our VE per cycle, the one that gave us 2,4 times 10 to the exponent of -3 cubic meters per cycle. Remember, we had this. You are not going to use the cubic meters per minute because if you use that, you have to convert again. So you use what is already in cubic meters per cycle. All right, let us make this the subject, guys. Cross multiply this and that is okay. Very sorry for that, guys. You see, this software is, like I said, I just hope we're gonna win. So in this case here, this has affected me so much, but I'm just hope we're gonna get back to where like I was saying, we have to make this the subject. All right, so that will be P1 V indicated times T4 is equal to, this will be P4 VE times what? T1. So since we want this, gonna divide by what? P1 and T4. So we remain with what? The induced, which is gonna be P4 times VE T1 over what? P1 T4, since we have divided by P1 T4. All right, so the advantage is that we calculated these ones. So it's just a matter of what? Of substituting our values. P4, everything we have. Remember our P4 was 5,8 megapascal, which gave us 5,800. So that's 5,800. Like I said, VE, since our values are given or are needed in cubic meters per cycle, we are supposed to use the VE that we calculated, the one that was in cubic meters per cycle, which is 2,4 times 10 to the exponent of -3. Don't use the one that you're given there. Times T1, we have got T1, which is 298,5 Kelvin, over P1. We have got also this part, P1 here, which is 90 kilopascal times T4. Remember, we calculated our T4. It was 417, if you still remember, 417,9 Kelvin. So that was going to give us the volume, which is in cubic meters per cycle. Since this is used in cubic meters per cycle, it means also our answer is going to be in cubic meters per cycle. So that's the induced volume is going to be given as a 0,11. That's 047. So it's going to be just a 0 there. Cubic meters per cycle, like that. All right. So we have to be careful. What are we supposed to calculate? How do we calculate that? All right. What are we supposed to calculate and how do we calculate from the information that we are given? So that was the idea then. Then the other part was for the swept volume, again, in cubic meters per cycle. Then for the swept volume, we've got a relationship here that we are given. Remember, there's a relationship, but this relationship is going to limit us because we do not have the clearance volume. They also want to calculate the clearance volume later on. So meaning to say this is limited. So how can we calculate the swept volume? All right, remember what we did on the high pressure cycle. If you still remember that question, when we worked with this high pressure where we're given, where we used its volumetric efficiency. Like I said, guys, my video has been affected. So now my information has been taken. I don't know how, but I'm just going to try to explain better. Remember, on the low pressure there, we were given the volumetric efficiency of the low pressure, which was given as, that was 0,96. That was 0,96, if you still remember. And I talked about the volumetric efficiency at each stage, all right? There we used the one that was on the high pressure because it was for the high pressure. This time, these questions are for the low pressure. So meaning to say, from that volumetric efficiency, remember we said our formula for the volumetric efficiency, we saw that from our formula sheet, it was what? The effective volume over the swept volume. So this time we are dealing with the low pressure cylinder. So we have to take the volumetric efficiency for what? For the low pressure cylinder, which is 0,96. As we need to calculate what? The swept volume. So that means 0,96 is equal to, which value are we going to use? We need our answer in cubic meters per cycle. So we have to use the effective volume, the one in cubic meters per cycle, the 2,4 times 10 to the exponent of what? Times 10 to the exponent of -3 over the swept volume. So that's the idea there. So how can we calculate this? We can cross multiply. That's 0.96 times VS, which is 0.96. That's 0.96 times VS is equal to 1 times this value. That's 2.4 times 10 to the exponent of -3. Remember, what you want there is to calculate VS. So what do? You divide by what? 0.96 both sides. So this is going to give us the value of VS. And that's our swept volume. Since this is in cubic meters per cycle, our answer is also going to be in cubic meters per cycle. So you're going to get something like 0.11458, which is going to be 115 to 3 decimal places. And that's cubic meters per cycle. So just also cross-check with your calculations there. All right. And another part that we asked was to calculate the clearance volume. Remember, they also wanted us to calculate the clearance volume, and the last one was the cylinder volume. All right. So for the clearance volume, now we can use this relationship, because remember, this relationship was for the low cylinder. All right. This was just given. All right. This relationship that the clearance volume is 4.5 for all the given stages. So we can take that as an advantage. So we are given that the clearance volume is equal to 4.5% of the swept volume. So at the low pressure cylinder, we have calculated the swept volume here, and we're just going to substitute. So that's VC. Remember this as a decimal. If we divide by 100, that's 0.045 times the swept volume. Since we need our answer in what? Cubic meters per cycle, we have to use the swept volume in cubic meters per cycle, 0.115 cubic meters per cycle. That's our answer is going to be in what? Cubic meters per cycle also. So there it was just straightforward, taking the information that you're already given. So that was going to give you 5.175 times 10 to the exponent of -3 cubic meters per what? Per cycle. What's the idea there? That's the idea. All right. Then the last question was to calculate the cylinder volume. If you still remember all our information, it was the cylinder volume. So for the cylinder volume, the cylinder volume is the sum of the clearance volume and the swept volume. The clearance volume we calculated in cubic meters per cycle, 5.175 times 10 to the exponent of -3, plus the swept volume in cubic meters per cycle, 0.115 cubic meters per cycle. So this was going to give us the volume of the cylinder at the low pressure from the low pressure values that we are given here. All right, so that's the formula. So this was going to give you 0.120175, which is 120 to 3 decimal places, cubic meters per cycle. So that is it there. All right, that is the idea there. So guys, we have to be careful. Your information that you are given, how to apply your information. So this is 20 marks on this question. Like I said, I'm very sorry guys for this video. You know, this software, when you are using, when you are having those long videos like this one, it just affect, I don't know, it just misbehaves. But I just hope you have the idea. If there is any part that is not clear, let me know on the comment section so that we can work on that on our next class. But for now, that's it guys, from Maths Zone African Motives. Till we meet again.